One of the major features of relational databases is their ability to join two tables together. Understanding how Oracle performs these joins is important to help us understand the performance impact of different join operations on your SQL statement. The first join operation we're going to take a look at is a nested loops join. This is one of the most common joins used in Oracle, especially when you're joining smaller data sets together. In a nested loops join, you have two row sources. On the slide, these row sources are shown as tables, but these two row sources don't necessarily have to be tables. They could be any data set that is the result of a prior operation, like a previous join operation. What Oracle will do is it will designate one of these row sources as the driving source. Usually, but not always, this will be the smaller of the two data sets. Then Oracle will iterate through each row in the driving source, checking the inner source for matching rows. The name nested loops joins comes from the fact that when Oracle is iterating over the driving table, this is like the outside loop in a nested loops algorithm. So in this outside loop, Oracle will get a row from the driving table, and then for each row, we'll execute an inner loop, looking for rows that match the driver row inside of this loop. If matching rows are found, then Oracle will output the joined row into the output data set. From a performance standpoint, this works well if the size of the driving table, shown as the external row source in this pseudocode, is small. It is also important that for each row Oracle processes in the outer loop, Oracle is able to efficiently look up matching values in the inner row source, like by using a selective index. Where the nested loops join runs into trouble is if both data sets are large, or if there is not an efficient way to look up a row from the external row source in the inner row source. If there's not an index on the inner row source that can be used, then Oracle will have to perform a sequential scan of all of the data in the inner row source. If this inner row source is small, that will be acceptable for performance. But if both our row sources are large, the number of comparison operations that will have to be performed is the number of rows in the inner source multiplied by the number of rows in the outer source, and as you can see, these numbers get big in a hurry. So it is really the size of the two row sources and the ability to efficiently perform a lookup in one of the row sources that drive the performance of the nested loop join. The second join operation we're going to look at is a hash join. A hash join is the most common type of join used when you're joining two large data sets. What Oracle is going to do is take one of the row sources that needs to be joined, usually the smaller one, and build a hash table from this row source. The key for this hash table will be a value calculated from the columns in the join condition. Then, Oracle is going to iterate through the other row source and probe the hash table it just built for matching values. When a match is found, this row will be included in the result set. Oracle will look to perform a hash join when there is no suitable index that can be used in a nested loops join. Since no suitable index exists in order to probe one of the data sources, what Oracle is doing is building its own data structure in memory, the hash table, that can be used to perform the join operation. And this is one of the keys for hash join performance. First, Oracle has to build the hash table, so Oracle is expending processing resources to do this. Second, if the hash table Oracle needs to build is large enough, it may not fit into memory on the Oracle server, meaning that Oracle will have to cache part of the hash table to its temp table space. Consequently, Oracle will incur cost for physical I/O during the join process when it needs to read and write parts of the hash table to disk. That being said, hash joins are often the most efficient join operation when large data sets are involved. Let's think of an example where we have two row sources, each containing 10,000 rows, and we want to join these two row sources. If Oracle was to perform a nested loops join, and there was not an index on the join condition that could be used, Oracle may have to perform up to 100 million comparison operations during the course of the nested loops join. I say up to because internally, Oracle contains some optimizations to account for things like repeated key values. Still, if no index is available, the number of comparisons is going to be relatively high. Using a hash join operation, we'll incur a cost to read through one of the row sources and put its data into a hash table. But now, when we iterate through the second row source, we can perform an efficient hash table lookup, and we'll only need to do this 10,000 times. And this is the essence of how a hash join works. You're investing some resources in building a hash table up front, but this allows the subsequent probing operation that must be performed to be done so much more efficiently. The final join type that we will look at is a sort-merge join. A sort-merge join is used when each of the row sources that Oracle is trying to join is in sorted order, and that sorted order matches the join condition that is applied. In some cases, the rows in the row sources are already in sorted order because they've been read from an index. In other cases, Oracle will perform a sort against the rows in one or both of the row sources. Then, once the rows have been sorted, Oracle can perform a merge operation between the two data sets, and this merge is very efficient because the rows are already sorted. The performance driver for the sort-merge join is usually the sort operation. If the rows can be read from an index, and therefore are already sorted, then Oracle doesn't have to perform a sort, so this saves time and resources. If, on the other hand, Oracle does have to perform a sort operation against one or both of the row sources, the Oracle Optimizer has to account for this cost in its calculations when deciding whether or not to use a sort-merge join. Obviously, it is more expensive to sort large data sets than small ones, and so if the data set is large and unsorted, oftentimes Oracle will opt for a different join operation. When you're evaluating join operations in execution plans, what is it that you should look for? A good first question to ask is which table will Oracle choose to access first, because this table will drive any further join operations and the rest of your SQL statement. For this table that is driving the rest of the SQL statement, we want it to be as selective as possible. That is, to only get back the rows that we really need. If this driving table comes back with a lot of rows that are subsequently going to be thrown away when the table is joined to other tables, Oracle won't be able to use a nested loops join, which is very efficient at joining small data sets, and instead will be forced to resort to something like a hash join, where it needs to build a hash table in memory. The second question to ask yourself is if there are any indexes available on columns in the join condition for both tables in the join. If there are indexes, and these indexes are selective, Oracle can use those during the join process to look up matching rows between the two tables. As we have already seen in the prior section, anytime data can be accessed through using a tree structure of an index rather than a sequential search, this is going to be much faster. The final question to ask yourself is if your SQL statement really needs to join to a table or not. Many times in my career, when I've been asked to help tune SQL statements, I found complex queries joining to tables where it turned out that the data from the table wasn't even used in the application process that was running the SQL statement. There are also times that if you're using multi-column keys in your tables, or perhaps that you have done some slight denormalization of your table structure, that you may be able to skip over joining to a linked table and instead join directly to the table that has the data you need. So as with all other operations, try to keep in mind the big picture of what your application and your SQL statement is trying to accomplish, and make sure that you really need to access each and every table in your SQL statement.